Hey, ladies and gentlemen, I want to talk about this can right here. This happens to be a can of Trader Joe's organic pinto beans, but it could be pretty much any can because one thing you've probably noticed if you've ever been to the grocery store or looked in your pantry is that almost every can is the exact same shape and size. And I don't mean that they're all cylinders. I mean that they are a very specific cylinder with a specific height and a specific radius. And we're going to talk a little bit today about why. So here we go. Problem number 4. The Felon Mitchell Limited Liability Corporation, LLC, has gotten into the soup business. They are banking on this being a big year for soup. Who doesn't like a warm bowl of soup? Am I right? A standard can of soup is 12 ounces, which, if you convert ounces into milliliters, is 355 milliliters of soup. A reason we want this to be in milliliters is that would be equivalent to 355 cubic centimeters, and we're going to be measuring the sides of the can. The process of manufacturing the tin for your can is expensive. Not to make one can, but when you're making thousands of them, like every little scrap of tin could end up to being millions of dollars, both from a financial perspective and from an environmental perspective. Felon Mitchell Corp wants to find the dimensions of the 355 milliliter can that minimizes the can's surface area. This means you want to find the ideal radius and height. And we're going to follow the 6 steps that you do when you are doing optimization. So, optimization, you remember this from our last unit, is built around following these 6 steps. And we know that this is going to be an optimization problem because it asks us to minimize. So, here we go. I'm going to follow these 6 steps. Step number 1 is to draw a picture of the physical situation. And the physical situation we're looking at is we got ourselves a can here. Here are the bases of the can. Both of those bases are circles. And then it has a height. Both the surface area and the volume of the can are defined by 2 quantities. The first is this right here, the radius. And the second is this, its height. And so that's step 1. We're looking at a can. We want to choose the dimensions of the radius and the height. Step number 2 is to write an equation for the thing that you want to minimize. And this problem asked us to minimize the amount of surface area. So if you take like the lid and the bottom and then this distance around, we want to make that surface area as small as possible. So I'm going to write that equation this way. Surface area of the can is equal to, it's got 2 lids, right? And both of those lids are circles. So that's pi r squared. And there's 2 of those. Plus, now for the lateral face of the can, I want to point out that this is actually just a rectangle, where the height is the height of the can, and the base is, watch me wrap it around here, equal to the circumference of the can. So the lateral face is 2 pi r, that's the circumference, multiplied by the height. Now, I showed you how to calculate this because I wanted to, but you don't have to memorize that. In fact, you'll notice that if you look at the packet, that surface area formula is given to you. Okay, so there's our surface area. Now, the third step, anytime you are doing an optimization problem, is to write one or more constraint equations. And here's our constraint equation. It involves the volume. Now, the volume of a cylinder is pi times the radius squared times the height. And we know what our volume needs to be. It needs to be 355. So 355 equals pi r squared h. That's our constraint equation. Now, the next thing that we do is we take that constraint equation and we use it to take our minimizing equation and get it down to one variable. Right now, we got two variables. We've got r, see that? Do you see that we've got radius in two places? And we've also got h. So what I'm going to do is get rid of that h by taking our constraint equation and dividing both sides by pi radius squared so that we arrive at the height has to be equal to 355 over pi r squared. I'm going to bring that up here. I'm going to plug it in. So now the surface area is this plus 2 pi r times this. We're going to do a little simplifying. This pi and this pi, they cancel. This radius and this radius, they cancel. And we get down to the surface area is simply 2 pi r squareds plus 2 times 355 would give us 710 over r. That's the equation we want to minimize. Now you can see why this is related to rational functions. Notice that we have an r in the denominator. All right, so let's go graph this. By the way, that was step 4. Step 5 is to graph and find the minimum. So I can tell that this equation is going to have a vertical asymptote when the radius is equal to 0 right here. Because plugging 0 in for r would be a no-no. I can also tell that as the radius gets really, really big, this term is going to grow really, really big. So our graph is going to have to drop and then head off to positive infinity as r becomes very large. Now, do we have to be able to figure that out on our own? Not necessarily, but it helps. Let's grab a calculator. Let's plug this in. Oh, I'm plugging it into the wrong place. Let's plug it in right here. This thing's driving me nuts. Delete. There we go. Plus 710 over x. And we might go over here to the table and just test a few values. Okay. 0, I get error. That shouldn't be a surprise. 1, I get 716. 2, I get 380. 3, I get that. 4, 5, 6, 7, 8. Okay, so it looks like it's the surface area, which is y, is dropping. It's hitting a minimum somewhere between 3 and 5. And the y values look like they should probably go up to about 700 or so. So I'm going to do this. I'm going to say x goes from 0 to 8, and y goes from 0 to 700. And then I'm going to hit the graph. There it is. Second calc, minimum. Move to the left of the minimum. Move to the right of the minimum. Hit enter. There's our minimum. So our minimum occurs at 3.84, 277.5. Let's make sure we answer the question. The question asks us for the dimensions. This, by the way, is the sixth step. To always make sure that you answer the question that you were asked. And here, let me bring the problem back for a second. Problem said we want to find the dimensions of the can that minimizes the surface area. So that means that we need a radius and we need a height. Well, this is the radius. It would be 3.84 centimeters. If we want the height, I think the easiest way to find it would be to use this equation right here and plug our radius in there. So I'm going to plug in 355 over pi times 3.84 squared. And let's see what that gives us. 355 divided by, in parentheses, pi times 3.84 squared is 7.66. Okay, there's the dimensions that would use the least amount of tin. Let's do one more together. Let's try number 5. What does number 5 say? Rectangles are some of my favorite shapes. Triangles are too pointy, but pentagons are awfully round. Consider all rectangles with an area of 182 square feet. Okay. So it says, give 3 examples of rectangles that would have an area of 182 square feet. Let's see. So if I know that this is my base, this is my height, and this is 182, I can probably just pick some measurements. So let's suppose that the base was only equal to 2 feet. Then wouldn't the height have to be equal to, where did I put my calculator? The height would have to be 2 times h is this. So 182 divided by 2 is 91. Also, if the base was 4 feet, then the height would have to be 182 divided by 4, so 45.5 feet. Also, if the base was 10 feet, I'm just making up numbers now, then h would have to be 18.2 feet. There are bazillions and bazillions and bazillions of different rectangles that have this measurement. So now here's where it gets interesting. B says, write an expression for the perimeter of this rectangle in terms only of its height. Well, the perimeter of my rectangle is equal to an H and an H and a B and a B. So it'd be equal to 2 H's plus 2 B's. And it says to write it in terms of only its height. So we're going to have to use a second equation. Our second equation goes like this. We know that 182 is equal to the base times the height. So we could solve this for base. We could say base is equal to 182 divided by height, which is exactly what I was doing here, right? I was taking the base and plugging it in to get the height. We could take that and bring it in and plug it in right here. And now the perimeter is equal to 2 times the height plus 2 times 182 over h, which means that the perimeter would be equal to 2 h's plus whatever that number ends up being. What is that going to be? 364 over h. So there's your answer to B. Part C says, Find the dimensions of the rectangle that has the least perimeter. What is the least perimeter? So for C, let's draw a picture. You know, this picture is going to be really similar to the one that we did for the can problem just a minute ago. Uh, and the reason we know that is because first, see how once again our variable is the height this time, can't be zero. Zero's on our no-no list. So just like the last one, we're going to have a vertical asymptote here at 0. And then if this is our perimeter, I can see that because there's this plus 2h on the end here, while it's going to hug the asymptote near 0, it's eventually going to turn around and head off to positive infinity because of that term. So we just need to figure out this point. Grab your calculator. In the calculator, let's put in 2x plus 364 is divided by x. And then I'm going to go to the table and just look at some values. All right, so as the height is getting bigger, let's see what's happening here. It seems like it continues to get smaller for a while. 10, 20. Oh, that's as far as I can go. Let's go. Let's go 10, 20, 30, 40, 50, 60, 70, 80. Delete, delete. Okay, now we can see it. So the value is dropping until, actually, it looks like it's somewhere before 10, doesn't it? What does it look like at 5? Ah, okay. So somewhere between 5 and 20, we're going to hit some kind of minimum, and then it's going to start to come up. So for my x values, I might go something like from 0 to, I don't know, one of these numbers around here, 0 to 50. And then for my y values, it needs to go at least up to, I don't know, it looks like the minimum is going to be somewhere in the 50s. So maybe I'll go something like from 0 to bigger than 50. I'll go to 100 and hit graph. Okay. And you can see that this looks like this. And we hit second calc. We go to minimum. And our minimum is going to be somewhere between here and here. And I hit the enter button. Our minimum is 13.49, comma 53.96. That's a 3. Let's make sure we answer the question. It says find the dimensions that give us the least perimeter. What is the perimeter? Okay. So our dimensions would be the height is 13.49 feet, and the base would be, using this equation right here, equal to 182 divided by 13.49, which gives us, hey, what do you know? 13.49 feet. In other words, if we want the minimum perimeter, then the shape should be a square, right? Because the base and the height are the same. We were asked for the perimeter as well. And that would be this right here. That would be 53.96 feet. Okay. So I've done number 4 and number 5 with you. I now want you to sit down and do number 6 and number 7. And then you're all done with applications.